So in 1781, an English composer, technologist, and astronomer called William Herschel noticed an object on the sky that didn't quite move the way the rest of the stars did. And Herschel's recognition that something was different, that something wasn't quite right, was the discovery of a planet, the planet Uranus. A name that has entertained countless generations of children, but a planet that overnight doubled the size of our known solar system. Just last month, NASA announced the discovery of 517 new planets in orbit around nearby stars, almost doubling overnight the number of planets we know about within our galaxy. So astronomy is constantly being transformed by this capacity to collect data. And with data almost doubling every year, within the next 2 decades, we may even reach the point, for the first time in history, where we've discovered the majority of the galaxies within the universe. But as we enter this era of big data, what we're beginning to find is there's a difference between more data being just better and more data being different, capable of changing the questions we want to ask. And this difference is not about how much data we collect, it's whether those data open new windows into our universe, whether they change the way we view the sky. So what is the next window into our universe? What is the next chapter for astronomy? Well, I'm going to show you some of the tools and the technologies that we're going to develop over the next decade, and how these technologies, together with the smart use of data, may once again transform astronomy by opening up a window into our universe, the window of time. Why time? Well, time is about origins, and it's about evolution. The origins of our solar system, how our solar system came into being. Is it unusual or special in any way? About the evolution of our universe, why our universe is continuing to expand. What is this mysterious dark energy that drives that expansion? But first, I want to show you how technology is going to change the way we view the sky. So imagine if you were sitting in the mountains of northern Chile, looking out to the west towards the Pacific Ocean, a few hours before sunrise. This is the view of the night sky that you would see. And it's a beautiful view, with the Milky Way just peeking out over the horizon. But it's also a static view. And in many ways, this is the way we think of our universe, eternal and unchanging. But the universe is anything but static, constantly changes on timescales of seconds to billions of years. Galaxies merge, they collide at hundreds of thousands of miles per hour. Stars are born, they die, they explode in these extravagant displays. In fact, if we could go back to our tranquil skies above Chile, and we allow time to move forward to see how the sky might change over the next year, the pulsations that you see are supernova, the final remnants of a dying star, exploding, brightening, and then fading from view. Each one of these supernova 5 billion times the brightness of our sun. So we can see them to great distances, but only for a short amount of time. 10 supernova per second explodes somewhere in our universe. If we could hear it, it would be popping like a bag of popcorn. Now, if we fade out the supernova, it's not just brightness that changes. Our sky is in constant motion. This swarm of objects you see streaming across the sky are asteroids as they orbit our sun. And it's these changes and the motion, and it's the dynamics of the system that allow us to build our models for our universe, to predict its future, and to explain its past. But the telescopes we've used over the last decade are not designed to capture the data at this scale. The Hubble Space Telescope, for the last 25 years, it has been producing some of the most detailed views of our distant universe. But if you tried to use the Hubble to create an image of the sky, it would take 13 million individual images, about 120 years to do this just once. So this is driving us to new technologies and new telescopes. Telescopes that can go faint to look at the distant universe, but also telescopes that can go wide to capture the sky as rapidly as possible. Telescopes like the Large Synoptic Survey Telescope or the LSST, possibly the most boring name ever for one of the most fascinating experiments in the history of astronomy. In fact, proof, if you should need it, that you should never allow a scientist or an engineer to name anything, not even your children. We're building the LSST. We expect it to start taking data by the end of this decade. I'm going to show you how we think it's going to transform our views of the universe. Because one image from the LSST is equivalent to 3,000 images from the Hubble Space Telescope. Each image 3.5 degrees on the sky, 7 times the width of the full moon. Well, how do you capture an image at this scale? Well, you build the largest digital camera in history, using the same technology you find in the cameras in your cell phone or in the digital cameras you can buy in the high street, but now at a scale that's 5.5 feet across, about the size of a Volkswagen Beetle, where one image is 3 billion pixels. So if you wanted to look at an image in its full resolution, just a single LSST image, it would take about 1,500 high-definition TV screens. And this camera will image the sky, taking a new picture every 20 seconds, constantly scanning the sky, so every 3 nights we'll get a completely new view of the skies above Chile. Over the mission lifetime of this telescope, it will detect 40 billion stars and galaxies. And that will be for the first time we'll have detected more objects in our universe than people on the Earth. Now we can talk about this in terms of terabytes and petabytes and billions of objects. But a way to get a sense of the amount of data that will come off this camera is that it's like playing every TED Talk ever recorded simultaneously, 24 hours a day, 7 days a week, for 10 years. And to process this data means searching through all of those talks for every new idea and every new concept, looking at each part of the video to see how one frame may have changed from the next. And this is changing the way that we do science, changing the way that we do astronomy, to a place where software and algorithms have to mine through this data, where the software is as critical to the science as the telescopes and the cameras that we build. Now, thousands of discoveries will come from this project. I'm just going to tell you about 2 of the ideas about origins and evolution that may be transformed by our access to data at this scale. In the last 5 years, NASA has discovered over 1,000 planetary systems around nearby stars. But the systems we're finding aren't much like our own solar system. And one of the questions we face is it just that we haven't been looking hard enough? Or is there something special or unusual about how our solar system formed? And if we want to answer that question, we have to know and understand the history of our solar system in detail. And it's the details that are crucial. So now, if we look back at the sky, at our asteroids that were streaming across the sky, these asteroids are like the debris of our solar system. The positions of the asteroids are like a fingerprint of an earlier time when the orbits of Neptune and Jupiter were much closer to the Sun. And as these giant planets migrated through our solar system, they were scattering the asteroids in their wake. So studying the asteroids is like performing forensics on our solar system. But to do this, we need distance. And we get the distance from the motion, and we get the motion because of our access to time. So what does this tell us? Well, if you look at the little yellow asteroids flitting across the screen, these are the asteroids that are moving fastest because they're closest to us, closest to Earth. These are the asteroids we may one day send spacecraft to mine them for minerals. But they're also the asteroids that may one day impact the Earth, like happened 60 million years ago with the extinction of the dinosaurs. Or just at the beginning of the last century when an asteroid wiped out almost 1,000 square miles of Siberian forest. Or even just last year as one burnt up over Russia, releasing the energy of a small nuclear bomb. So studying the forensics of our solar system doesn't just tell us about the past, it can also predict the future, including our future. Now, when we get distance, we get to see the asteroids in their natural habitat, in orbit around the Sun. So every point in this visualization that you can see is a real asteroid. Its orbit has been calculated from its motion across the sky. The colors reflect the composition of these asteroids. Dry and stony in the center, water-rich and primitive towards the edge. Water-rich asteroids which may have seeded the oceans and the seas that we find on our planet when they bombarded the Earth at an earlier time. Because the LSST will be able to go faint and not just wide, we'll be able to see these asteroids far beyond the inner part of our solar system. To asteroids beyond the orbits of Neptune and Mars, to comets and asteroids that may exist almost a light year from our sun. And as we increase the detail of this picture, increasing the detail by factors of 10 to 100, we'll be able to answer questions such as, is there evidence for planets outside the orbit of Neptune? To find Earth-impacting asteroids long before they're a danger, and to find out whether maybe our sun formed on its own or in a cluster of stars. And maybe it's this sun's stellar siblings that influenced the formation of our solar system, and maybe that's one of the reasons why solar systems like ours seem to be so rare. Now, distance and changes in our universe. Distance equates to time, as well as changes on the sky. Every foot of distance you look away, or every foot of distance in an object is away, you're looking back about a billionth of a second in time. And this idea, or this notion of looking back in time, has revolutionized our ideas about the universe. Not once, but multiple times. The first time was in 1929, when an astronomer called Edwin Hubble showed that the universe was expanding, leading to the ideas of the Big Bang. And the observations were simple. Just 24 galaxies and a hand-drawn picture. But just the idea that the more distant a galaxy, the faster it was receding, was enough to give rise to modern cosmology. A second revolution happened 70 years later when two groups of astronomers showed that the universe wasn't just expanding, it was accelerating. A surprise like throwing up a ball into the sky and finding out the higher that it gets, the faster it moves away. And they showed this by measuring the brightness of supernova and how the brightness of the supernova got fainter with distance. And these observations were more complex. They required new technologies and new telescopes because the supernova were in galaxies that were 2,000 times more distant than the ones used by Hubble. And it took 3 years to find just 42 supernovae, because a supernova only explodes once every 100 years within a galaxy. 3 years to find 42 supernovae by searching through tens of thousands of galaxies. And once they collected their data, this is what they found. Now, this may not look impressive, right? But this is what a revolution in physics looks like. A line predicting the brightness of a supernova 11 billion light years away, a handful of points that don't quite fit that line. Small changes give rise to big consequences. Small changes allow us to make discoveries, like the planet found by Herschel. Small changes turn our understanding of the universe on its head. So 42 supernova, slightly too faint, meaning slightly further away, requiring that a universe must not just be expanding, but this expansion must be accelerating, revealing a component of our universe which we now call dark energy, a component that drives this expansion and makes up 68% of the energy budget of our universe today. So what is the next revolution likely to be? Well, what is dark energy and why does it exist? Each of these lines shows a different model for what dark energy might be, showing the properties of dark energy. They all are consistent with the 42 points, but the ideas behind these lines are dramatically different. Some people think about a dark energy that changes with time, or whether the properties of the dark energy are different depending on where you look on the sky. Others make differences and changes to the physics at the subatomic level. Or they look at large scales and change how gravity and general relativity work. Or they say our universe is just one of many, part of this mysterious multiverse. But all of these ideas, all of these theories, amazing, and admittedly some of them a little crazy, but all of them consistent with our 42 points. So how can we hope to make sense of this over the next decade? Well, imagine if I gave you a pair of dice, and I said you wanted to see whether those dice were loaded or fair. One roll of the dice would tell you very little, but the more times you rolled them, the more data you collected, the more confident you would become, not just whether they're loaded or fair, but by how much and in what way. it took 3 years to find just 42 supernovae, because the telescopes that we build could only survey a small part of the sky. With the LSST, we get a completely new view of the skies above Chile every 3 nights. In its first night of operation, it will find 10 times the number of supernovae used in the discovery of dark energy. This will increase by 1,000 within the first 4 months. 1.5 million supernovae by the end of its survey. Each supernova a roll of the dice. Each supernova testing which theories of dark energy are consistent and which ones are not. And so by combining these supernova data with other measures of cosmology, we'll progressively rule out the different ideas and theories of dark energy until hopefully at the end of this survey, around 2030, we'd expect to hopefully see a theory for our universe, a fundamental theory for the physics of our universe to gradually emerge. Now, in many ways, the questions that I've posed are, in reality, the simplest of questions. Right? We may not know the answers, but we at least know how to ask the questions. But if looking through tens of thousands of galaxies revealed 42 supernovae that turned our understanding of the universe on its head, when we're working with billions of galaxies, how many more times are we going to find 42 points that don't quite match what we expect? Like the planet found by Herschel, or dark energy, or quantum mechanics, or general relativity, all ideas that came because the data didn't quite match what we expected. What's so exciting about the next decade of data in astronomy is we don't even know how many answers are out there, waiting answers about our origins and our evolution. How many answers are out there that we don't even know the questions that we want to ask? Thank you.